Hi everyone. Today is reaction rates. We're going to learn about reaction rates. So this is our Unit 3 kinetics, and this will be lesson 3.2. Okay, so lesson 3.2, we are going to look at the concept of reaction rates. Okay, so when we think about the word kinetic, basically, if you think of kinetics, what do you think of? And some of you who have a physics background, you will be thinking of movement, right? Kinetic energy, for example, the energy due to movement. So the study of kinetics, relates to different fields. So the one I pulled out here is metabolic reaction. So this would be things like slow release of drugs, right? So when you take pain medication, it tells you to only take, maybe some sort of pill every 6 hours or so. So when that happens, that means that your body is digesting it and the pill is releasing the medicine at specific rates. And scientists would work on that. And this would fall under the field of kinetics to determine how fast these things are happening and all the different variables associated with that. Another example here is bone regeneration. So some of you will have broken a bone. I actually never have. Knock on wood, haha. So I haven't broken one yet, but my son's broken it twice, and he's only 10. But anyways, when you have a bone break, it heals itself, right? If it sets properly and we regenerate bone. And that happens in certain rates. And that's why we have specific timelines for casting and things like that. So again, these are rates of reactions happening. Another one could be rusting. This would be the automobile industry and engineers working in there. So how to slow down the rusting process here. Another one's spoiling and decaying of food. So that's a chemical reaction that's happening, a chemical change. So you'll see best before dates on here. Now these have to be determined experimentally by scientists. And so this would be that sort of stuff. So best before dates and expiry dates would fall under Canadian Food Inspection Agency. So this is CFIA. So not quite Agriculture Canada, but very closely linked. Actually, place I used to work for Agriculture Canada, and so we had a CFIA build office in our building when we were researching. Anyways, those are just some examples of kinetics and how that would apply to some different fields. Okay, so we're going to look at the rate of reaction in this concept. That's what we're looking at today. So we can define the rate. This is speed, right? So the speed at which reactants are used and or products are formed. And so an example I gave you here is an apple that's rotting, right? So this is our nice fresh apple here. And then over time, we see the apple rotting, right? And then it'll start the decomposition process. So this would have a certain rate associated with it. There would be different factors that could influence how fast or slow that would happen. And in lesson 3.1, we talked about some of those. And so looking at this, what do you think would be one that would slow that down? Yeah, maybe temperature could have an effect, right? If you put your apple in the fridge, it's gonna it won't ripen as quickly, right? So anyways, we're gonna talk more about factors that affect the rates of reaction later on. Okay, so when measuring a reaction rate, we look for observable changes, so things that we can see happening. So we can define rate as the change in x, and x being whatever variable you use, over a change in time. And so generally in science, when we have the term change, we can use the Greek delta, the triangle, so change in x over change in time. And this would be our general formula for rate here. So something is changing, some observable trait is changing in a certain amount of time. And that's how we're going to define our rates. Okay, so there's different ways to express this. We're going to go through a few here. The first one we're going to look at is when you see a solid appearing or disappearing. And so the example I gave you here is copper. So we have solid copper and silver nitrate. Some of you may have done this in your grade 10 or grade 11 year. Now, because you would have seen that this is a single displacement reaction here. So it's pretty impressive to do this. It's very expensive though, because this is silver nitrate is not a cheap chemical for the school to buy. It's very expensive. But what you would do, you would put a copper wire into a solution of silver nitrate, and then what you would see happen was the copper and the silver would switch places. So this would be a single displacement, and you'd see the silver collect. And as you can see it here, you can see that silver collecting on that copper wire, and then the copper goes into the solution then to make the copper nitrate here. So if we look at this, the rate then can be expressed as, and so we have rate can be expressed as grams of copper used per unit time, so how much copper was used up or in per unit time, or we could also say grams of silver produced over unit time. Either of those would be completely acceptable rates to use for this particular experiment. Now, another way we can look at rates or describe rates is color changes. So color varies with concentration. Again, you would have learned that in your grade 11 course, right? The more dark or saturated a color is, that would indicate greater concentration. So we know that copper nitrate is blue. Therefore, in the equation we just looked at, you can clearly see that this is clear, and then the blue color increases as we move across there. And so you could describe the rate as the appearance of the blue color there. So, or the rate is equal to the increase in concentration of copper nitrate per unit time. So CON(C'(N) stands for concentration there, okay? For gases, we can measure volume. So we've got this reaction here. We've got peroxide, and that's becoming decomposing into water and oxygen gas. And so for this particular example, we can have the rate expressed as the volume of O2 produced per unit time. So that would be, sorry, hold on. So that would be, and so again, some of you may have done this in your grade 10 year. Some teachers do this as a law of conservation of mass. So you've got your reaction in your Erlenmeyer, and then if you put a balloon on top of it here, you can collect the O2 gas here. So collecting that gas, you could express the rate of this reaction then as the volume of oxygen gas produced. Now, for gases in closed containers, we can measure changes in pressure. So if we look here, we've got hydrogen gas and nitrogen gas is yielding ammonia here, NH3. So looking at this, if we look at this very on a molecular level, so let's not think about the equation, let's think about what's actually in there. So how many molecules do we have on the reactant side? So this is the reactant side here, this is the product side. So how many molecules do we have? Yeah, and hopefully you've counted here. You've got 1, 2, 3, 4 molecules. And then how many molecules do we have on the right-hand side? We only have 2. So what do you think happens to the pressure then as this reaction is going to move forward? We're going from, 4 molecules here, so they're quite crowded together, to only 2 molecules. So what do you think happens to the pressure as time is moving on? Yeah, so the rate, so there's actually going to be a decrease in pressure as we move from 4 molecules to 2 molecules. So you can define this rate then. One way to describe it would be the decrease in pressure over unit time. And so this is only true for gases in closed containers though, so make sure you're aware of that little caveat there. Okay, now our lovely friend here, the mole, I told you guys the mole keeps coming back over and over again. We can look at stoichiometry for this. So it is found that the rate of a particular reaction, and it's written down below there, is 5 moles of hydrogen gas per unit time. So I'm asking you here to express this rate in moles of N2 used per unit time and moles of NH3 produced per unit time. So to do this, we're going to look at the mole ratio between them. So this is a balanced equation. If you were given a question like this, your first step would be to balance it. And now we're going to just figure this out here. So it tells me that I've got 5 moles of H2. And part A here is asking me to express the rate in moles of N2. So that's going to be my question mark there. Now, I'm just going to go ahead and use dimensional analysis just to keep this really clear for people. So I'm going to say moles of N2 is equal to, I know that I've got 5.0 moles of H2 per unit time, but I'm going to just multiply that by the mole ratio here. And so moles of H2 is going to go on the bottom, and moles of N2 will go on top. And the ratio between those is 1 to 3. So I end up with an answer of 1.7 moles of N2 per unit time. So that is part A there. So I just looked at the ratio, I looked at the rate that was given to me in hydrogen gas, and I just expressed it in terms of nitrogen gas using the mole ratio. So I can always go mole to mole that way. Now for part B tells you to express it in moles of NH3 produced. So I'm just going to use dimensional analysis to show the mole ratio again. So moles of NH3, again, I know that I've got 5.0 moles of H2, and then I can just multiply that by the mole ratio. So moles of H2 on the bottom, moles of NH3 on the top, and the ratio between them is 2 to 3. So I end up having 10 divided by 3, and I get an answer then of 3.3 moles of NH3 per unit time. Okay, makes sense? Good. Okay, so let's work through this example here. And ideally, again, pause the video here and try this one on your own maybe. Okay, so I'll work through this. So a 3.0 gram piece of zinc, so right away, 3.0 grams, is placed in a 0.2 molar solution of acetic acid. Okay, so this is 0.20 molar. After 45 seconds, no, actually, I didn't even need to do that. Never mind. 1.2 grams of the unreacted zinc remain. So find the average rate at which zinc was consumed in grams per second and then moles per second. So you want to just approach these with math eyes. These are really just word problems for math within a chemistry context, right? But you have you have the skills to do this at this point. So you just need to think that you've got 3 gram, so a 3 gram piece of zinc. That's my piece of zinc, 3 grams. You are going to place it into a solution. After 45 seconds, so time goes by, after 45 seconds, this piece now, sorry, I shouldn't have done that, hold on, erase. Okay, so after 45 seconds, this piece of zinc is now this big, so it's smaller, and you only have 1.2 grams of it remaining. So find the average rate at which zinc was consumed. So we started with 3 and we ended up with 1.2. So how much zinc was consumed? So hopefully you know that I'm going to go 3.0 subtract 1.2 to get 1.8 grams of zinc. So 1.8 grams of zinc was used in 45 seconds. Now the question is asking me though to find the rate in grams per second. So I'm in grams per 45 seconds. So how do I do that? Hold on one second. Sorry, guys. So how are you going to do that? For this one, you are going to, people set up their ratios differently. So I'm just going to work at the top here where I have space. So you know that you had 1.8 grams in was it 1 point? Yeah, in 45 seconds. So how many grams is it per 1 second? So you just cross multiply and divide. So 1.8 grams divided by 45 seconds. Hold on. So 1.8 divided by 45, and you're going to get 0.04. So part A then, it's going to be 0.04 grams of zinc per second. So people, like I said, people have this look differently. It doesn't matter how you do it. Just make sure you have your own way of understanding that. And then part B here, yeah, I did leave myself space. Okay, so part B is to find that rate in moles per second. So part B, I want to find it in moles per second. Now, I just said that it's 0.04 grams per second, right? So I need to convert this into moles. Do you remember how to do that? So moles of zinc, moles of zinc is going to be equal to 0.04 grams. You know what, I'm just thinking, I don't think I paid attention to sig figs there, did I? Yeah, I need another 0 there, sorry. There we go. Okay, so 0.040 grams of zinc, and I want to convert that into moles, so I'm going to divide by the molar mass here. And the molar mass of zinc is 65.4. And so I get my answer now. It's going to be 0.04 divided by 65.4, and I get an answer of, hold on, yeah, here we go. And I get an answer of, it's in scientific notation, but that doesn't matter, 6.12 sig figs here, times 10 to the negative 4 moles per second. So that was the rate that I was looking for there. Okay, so there's your answer there. Now, important thing to note, the reaction rate does not equal the whole reaction time. So it may take a while for something to happen, but that does not equal the rate, right? So keep that in mind. Okay, so reaction rate is a change over time, and the whole reaction time is the amount of time for a reaction to occur. So those are not equal to each other. Just make sure you understand the difference there. Okay, you can take a look at exercise 1. The answer key is posted, so you can take a look at that. Sorry, it's pretty sloppy. My apologies. I need to find the time to do that, to recopy it. But exercise 1, try that, and then tomorrow we'll move on to our next topic. Thanks, everyone.